My name is Colin Strieby, and this will be my presentation. This is a brief history of cryptography and its applications in computer engineering. Alright, so what is cryptography? Cryptography is the study of encrypting information. Anytime a party needs to send information, like a message, to another party securely and privately without other people being able to know what they're saying, that is cryptography. Cryptanalysis is the parallel field, and it involves the study of how to decrypt these secret messages. Alright, so cryptography has been around for a very, very long time. Almost as long as people have been able to communicate with one another, there's been a need to communicate privately. The first appearance was in 1900 BC in ancient Egypt. They found some hieroglyphics that had evidence of a few different ciphers. It was never really clear if this was to hide information or if it was simply like a word game that literate, educated people were playing. But there were other examples from back then. They found a stone tablet with a recipe for pottery glaze at around 1500 BC. Presumably it had some commercial value that the owner of the recipe didn't want other people to know. The ancient Greeks used different word ciphers and alphabetic ciphers to encrypt battle plans, and it's easy to see the need to keep that information out of the hands of the enemy. But all these methods back then were very ad hoc. It was very difficult to determine the strength of any given encryption. It was impossible to say how strong your encryption was, how easy it would be to decrypt, so it wasn't very advanced. Here we have an example of one type of cipher that was used back then. This is a rail-fence cipher, which is a type of word cipher. A word cipher is any kind of algorithmic way of scrambling up the letters in a message. So I have an example right here. It usually involved some kind of key or algorithm that both parties would have. So the rail-fence cipher relies on a keyword, cat. The first thing that we do is we organize it alphabetically, so cat goes to ACT, and then all the letters as they're spelled out are assigned a number, incrementing as you go. So 1, 2, 3. So now if we go back to our original word cat, the corresponding numbers would be 2, 1, 3. So now we take our message. The message in this example is hello world, and we write out our columns 1, 2, 3, and we just write our message out left to right. So as you can see, the keywords serve two purposes. One, it told people how long the columns had to be, like the dimensions of the grid that you were filling in, and it also told people the ordering of the columns. So as you can see, we take the keyword cat and we swap out the columns according to however the letters are organized. So as you can see, we swap it out there. And then to get our encrypted message, we just read it again left to right. And here we have that the final encrypted message. Now that looks pretty easy to break, and that's because it is. Cat would not be an ideal keyword, but for the sake of simplicity, I picked an easy one. The other type of cipher that was used was an alphabetic cipher. Now, a word cipher works by scrambling the letters. An alphabetic cipher works by swapping out the letters in some algorithmic way. So one very simple example that was used during the Roman times was referred to as the Caesar cipher. And what they would do is they would just take whatever letter in the message that you were on. So A would go three letters down. So A goes to B, C, D. B would go to C, D, E. C would go to F, so on and so on. So, and you could combine these ciphers to create a harder encryption. So if we took our first encrypted word, or our first encrypted message, which is right there, and applied a Caesar cipher, we would get this: a cork, razug. And to any person, and well, to most people looking at that, it would be kind of hard to figure out what was going on there. The next major advance that happened for the field of cryptography came from a man named Al-Kindi. He was a Muslim during the time of 800 AD, and he wrote a book of mathematics on something called, well, what is now called frequency analysis. Now, like I had said before, the way people had cracked these ciphers back then was very ad hoc. There was no procedural way to do it. And the frequency analysis, what it did was it analyzed the frequency of reoccurring symbols in the encrypted message. And it would also take into consideration the probability of certain letters being next to each other. Some letters never appear next to each other in some alphabets. And so, using that, and using a little math and a little algebra, he came up with a procedural way of cracking these ciphers. And as a result, these word ciphers became almost trivial until the Renaissance age, when a man named Leon Battista Alberti invented the polyalphabetic word cipher. Now, the polyalphabetic word cipher was a huge deal. It wasn't quite realized in his time, but what was important about it was, now instead of swapping out the letters in the same alphabet, what he did was he swapped out the letters in the message for a substituted alphabet. And the substituted alphabet could be a completely randomized alphabet. It could be the alphabet of another language. It could be any. It could be any arbitrary set of symbols. And so by doing this, it could make potentially solving these ciphers through a procedural way arbitrarily difficult by including an arbitrary number of symbols for your procedural analysis to work with. And one example of this would be the Kryptos statue. Kryptos is a statue standing outside of the CIA building, and it employs a polyalphabetic word cipher. And people have been able to crack the first three messages on the Kryptos statue, but the fourth remains a total mystery that even all of our intelligence and all of our computing machines today haven't been able to solve. Cryptography became increasingly important during World War I. This was the first major example where cryptography would make or break you. With the war came a subsequent war of our cryptographers versus their cryptographers. Whoever could crack the enemy message first would have a decided advantage. And it would often turn the tide of battle. The biggest example would be the Zimmermann telegraph. Zimmermann was the German officer of foreign relationships, and he wrote a telegraph to the president of Mexico trying to get Mexico involved in a war with America, and he promised that Germany would give Mexico the territories of Texas and New Mexico and all this other stuff. But anyway, we intercepted the message and we decrypted it, and this got America involved in the war much sooner than they originally would have. So, it's a very big deal. The Enigma machine. A lot of people have heard of the Enigma machine, and probably for good reason. It was pretty important. The Enigma machine was an electromechanical device employed by the Germans during World War II, and it was the first example of a machine implementing an algorithm for the sake of an encryption. And until this point, all encryptions have been done by hand, and you can imagine how, when it comes to algorithms, a machine could be much more efficient in producing and running these algorithms. So as a result, the encryptions were much, much harder to crack. Japan also had a similar machine, the JN25. So this was such a huge deal, this Enigma machine, that they put together a team of chess masters, mathematicians, engineers, including Alan Turing, the father of computer science, dedicated to the sole purpose of cracking this Enigma code. Luckily, they were successful, and the Germans didn't win the war. The RSA algorithm. The RSA algorithm gets its name from Ron Rivest, Adi Shemin, and Leonard Alleman. And the RSA algorithm was a big deal because until this point, all encryption and all these ciphers all used what were called symmetric keys. And what that meant, And what that meant was that the key that was used to encrypt the message was the same key that was used to decrypt the message. And getting this key securely from one person to another person was a big deal. In fact, the only reason we were ever able to crack the Enigma machine was because we raided a German U-boat and stole a copy of their machine and their tables and their key, and using some reverse engineering we were able to figure out the code in a sufficient manner to decrypt it. So getting these keys back and forth was this key sharing was a big problem. But the asymmetric keys kind of solved that through what's called one-way functions. Now, the way asymmetric keys work was, let's say I want to send a message to my friend Artem. What I do is we each have two keys, a public key and a private key. So I take my message and I encrypt it with Artem's public key. And then I take that encrypted message and also encrypt it on top of that with my private key. So now I take this doubly encrypted message and I send it to Artem. Now Artem receives my message and he decrypts his portion of the message with his private key. So he decrypts his public key with his private key, and then he decrypts my private key with my public key. And through doing this, he can be sure that I was the one who sent him the message, because no one has access to my private key, and only my public, and so the public key could only decrypt that. And no one else can obviously read the message, because no one has access to his private key except for him, or at least that's the idea. So in this way, private keys never need to be shared. And the way these keys are generated is by taking two huge prime numbers and multiplying them together. And the idea is that it's computationally very easy to multiply these two huge prime numbers, but factoring them into their two original prime numbers is very, very computationally intense and takes computers a very, very long time. And you can increase the size of the prime number, the prime numbers that you're multiplying arbitrarily, to make the computers take an arbitrarily long time. So that's asymmetric keys have their own problem though, in that decrypting two encryptions takes a lot longer than decrypting one encryption. So a common method that's done today is we'll use asymmetric keys to send a symmetric key to the person. So they only have to do that double encryption once to get the symmetric key. And now that the symmetric key has been sent securely, the rest of the message can be encrypted with a computationally easier to do algorithm. Alright, so what kind of jobs are there in cryptography for the aspiring computer engineer? The National Security Agency and the Central Intelligence Agency both hire a huge number of cryptographers. And while it's true that these positions are also competed for with mathematicians and computer scientists, there is a fundamental need to eventually encrypt these algorithms within computer networks, which requires engineers who understand these networks to implement. So really any facet that requires security or privacy or the sending of private information needs cryptography and engineers capable of working with it to some degree. So mobile devices, network security, online social network security, online banking, the list goes on. I'm sure that you can imagine. All right, so how does it compare to other engineering jobs out there in terms of pay? The average starting salary is comparable to that of what you would expect for an engineer, between 65 and 75K. And the average potential salary caps out at around $110,000, which might seem a little lower than what you would get from other career paths for engineering. But it's actually a little deceiving, because the NSA and CIA are actually the largest employer of cryptographers, and those are both public sector jobs. And public sector jobs usually means that a lower salary, but better benefits, better pension plan, better job security. So it's a fair trade-off, and cryptography remains a viable and appealing career choice for computer and electrical engineers. And that concludes my presentation. Thank you.